All right, let's go and get started. So just as a reminder, in the previous lecture, we started discussing learning-based approaches. I guess mostly to computer vision, but as we'll see, many of the techniques that we discuss will also be really relevant for other kinds of learning beyond computer vision. So it seems like the most, I guess, popular choice on the vote, at least as of right now, is reinforcement learning. So I think the material we covered today, unless things change, will be relevant to reinforcement learning. So I think that that'll be like a nice connection. So in the previous lecture, we assumed access to a data set of labeled examples. So this is the context of supervised learning. So we're going to continue to look at supervised learning for a little bit until maybe we talk about reinforcement learning or some other topic. And I guess just as a running example, we're using pedestrian detection as a kind of example problem, which might be useful for autonomous vehicles, for example. So in that context, we have a set of images with corresponding labels. So each image we're thinking of as a vector in some high dimensional space, the space of all images. And we're assuming access to, let's say, capital N different examples with corresponding labels. So if we're thinking about pedestrian detection, then the labels are maybe just binary, so 0 or 1. 1 if there is a pedestrian in the image, 0 if there's no pedestrian in the image. And the goal that we set for ourselves is to learn the mapping, so learn the function from images or image to the label. So what we want to be able to do is, given some new image that was not part of our training data set, we want to be able to say whether there's a pedestrian in the image or not. And the way we were going to learn this is given is with the help of the data set that we're given. So we're looking, at least for now, at a particularly kind of simple class of functions. So these are single layer neural networks. That I introduced in the previous lecture. So it's basically just a linear or affine function of the input passed through a nonlinear function, sigma. And we discussed some specific choices for sigma. So for example, sigmoidal activation. So it kind of looks like this. So the input to sigma, so this is sigma of z, and this is the input to sigma. So if z is very large and positive, then sigma outputs something that's close to 1. If z is very negative, then sigma outputs something that's close to 0. So that's just one particular choice. And inside that, we're just taking a dot product of some weight vector, which we're going to learn. Dot product of the weight vector with the image vector, and then just adding a bias term, b, and then passing that through the nonlinearity function. So yeah, I guess that's the structure of functions that we're going to look at. We're going to expand beyond this class of functions, but at least to begin with, I think this is a good place to start. And what we said in the previous lecture is the way we're going to learn the weights and the bias, so the w and b, those are the parameters in our function, the way we're going to choose them. So choosing w and b. So we're going to choose them by minimizing our training loss. And I guess the name for this is ERM, empirical risk minimization. And specifically, we defined training loss as the average loss. So the notation we used was L, which you can think of as a function of W and B. So for each setting of W and B, you get a particular training loss. So we define this as the average over the capital N examples that we have of little l of y predicted and the true label. And y predicted is sigma W transpose xi plus b. Right. So for every x, every image in our data set, we pass that through our function for a particular choice of W and B. We think of that as some kind of prediction. And then we compare that prediction with the true label, which in this case is maybe just 0 or 1. And depending on how far away the prediction is from the true label, we incur some loss, and then we just look at the average loss. And again, we looked at some specific example losses. So conceptually, maybe the simplest example is just a 0 or 1 loss. So you assign a loss of 0 if the prediction matches the label. What I guess we mentioned in the previous lecture is that this optimization problem, ideally you want it to be smooth in some sense. And we'll discuss exactly why in today's lecture. And for that reason, a better choice of L is the BCE loss. So that's the binary cross entropy loss. And so yeah, with a specific choice of loss function, this kind of is well defined. You can think of the training loss as a function of W and B, and we're going to find W and B that minimizes, that gives you the smallest possible training loss. So at least that's kind of the story we have up to now. We'll make some modifications later. So the plan for today is going to be to do two things. So first is think a bit more about how we do this optimization. So how do we find W and B to minimize the training loss? And the second thing we'll do is move beyond single layer networks to multi-layer networks. So we discussed some of the limitations of single layer networks in the previous lecture. So single layer networks are basically just doing template matching. So we have some template W, we compare that with the image and see how close the image is to the template. The other way to think about it is it's basically like linear classification. So we have a hyperplane in the space of all images that we're separating that space using. And if your example falls on one side rather than the other side, then you can classify the image accordingly. And we saw some simple examples where linear classification is not sufficient for separating different classes of examples. All right, so I guess that's roughly where we left off in the previous lecture. So let's start off with the first point. So how do we find W and B to minimize the training loss? Unfortunately, the magic cloth disappeared. It like fell. Yeah, I guess someone dropped it in there, and I don't have a way of taking it out. So we're gonna have to use the eraser again. Yeah, sorry. I should just buy my own, I guess. All right. Yeah, again, just ask me if things are not clear. And this thing is not a factorial again. It's just a piece of paint. All right, so how do we choose W and B. So the short answer, I guess, is using gradient descent. So I'll describe gradient descent and some of the I guess variants that people use in practice. So yeah, maybe you've seen gradient descent before, but I think it's still useful to just go through the basic idea and then discuss some of the modifications that people make for gradient descent. So I guess as we said over there, you can think of the training loss as a function of W and B, right? So each W and B that you pick, given a fixed training data set, leads to a particular training loss. So just for simplicity, consider a case where W, so the weight vector, is a scalar, and B is fixed. So we're just going to ignore B. So yeah, I guess this doesn't make like a ton of sense in practice. I mean, this is basically saying like little x, like the example, is just a scalar value. So we're just taking the space of x, which is a line, and we're just going to divide it up somewhere and say, like, if you fall on one side of the line, that's a 1. If you fall on the other side, it's a 0. But yeah, I think this is a good place to start, and then we'll make it more complicated. So in that case, the training loss maybe looks something like this. So here is just L of W, and W on the x-axis. So it could look like this. So depending on what choice of W you make, you might have a lower or higher training loss. And if you use the binary cross-entropy loss and the sigmoidal activation function, then this landscape is going to be smooth. It's not going to have discontinuities. So yeah, I guess in this case we can use gradient descent. To try to minimize the training loss. But before we do that, maybe let's just think about a kind of strawman algorithm, which is just random search. So the idea here is just very simple. So just choose, let's say, k random W's. So random according to some distribution that you pick. And just evaluate the training loss. For each one. And basically just pick the best one. So pick the W that gives you the minimal value for the training loss among this like randomly chosen set of W's that you picked. So this does something, right? I mean, you're just choosing a bunch of values randomly and just picking the one that happens to give you the smallest training loss. But this is not going to scale to anything beyond like a scalar W. Like if W was like truly high dimensional, so if you're working with images, then W has the same dimension as the images, then yeah, the chances that you'll get a good training loss just by randomly sampling a bunch of W's is pretty slim. But I guess the reason I mentioned this is we'll actually use something like this, combine it with gradient descent in a bit. Yeah, any questions? Go ahead, sorry.
Why would you want to pick them randomly instead of like uniformly disperse them across the available like range of W's?
Yeah, you could do that as well, especially if like W is a scalar. You can just like discretize and pick the one that gives you the smallest W. In a higher dimensional space, it might be harder to discretize. So this just randomly sampling a bunch of points you can do in like a higher dimension as well, like as opposed to having to discretize each dimension. Question?
Is the random search good for like integrating sometimes multi-dimensional that's not equal?
Exactly. Yeah. Yeah. So that's I guess that's the point I was going to make. So the other technique for trying to choose a W is to use gradient descent. So in this case, it's just I guess slope descent. So we're just working with or derivative descent, like one-dimensional example. So again, W on the x-axis, L of W on the y-axis. So yeah, what you do here is start off with some initialization for W. So pick a particular value of W. You look at the slope, so the derivative of L of W at that point. And then you take a step in the direction that's negative to the slope. So in this case, the slope is positive, so you move in the negative direction. So maybe you end up over here. So this is your new W. So this was the W you started with. You took a step to the left. So I guess just to write this down formally, so you start with some, let's say, random W, and then execute this for loop. So for, let's say, k equal to 1 through capital K for some number of iterations. Actually, did I? No, okay. Oh no, I used the same letter over there. Let me just change that. It's not the same K. Let's say this is like M or something. Yeah, so for K equal to 1 through K, we update our W. So W minus some scalar, gamma, multiplied by the slope. So D L dW. All right, so I guess there's a couple of things to think about. So what this is doing again is just trying to move in a direction that locally decreases the loss. So you look at the slope, you move in a direction that's negative, that's opposite to it. So one, I guess, important thing to think about here is what is the scalar parameter, this constant gamma. So gamma is known as the learning rate, or also known sometimes as the step size. And gamma has to be chosen kind of reasonably carefully over here. So I guess let's think about it. So if you choose a small gamma, what might be the concern there? Go ahead.
It's really small.
Yeah, it's really slow, right? So if you make it really small, you'll keep moving in the right direction, but it might take you a long time to converge. If you choose it to be very big, I guess what might be the concern there? Go ahead.
You'll like kind of bounce around before you actually like find an item. So.
Yeah, exactly. So you might go all the way from here to somewhere like over here, and maybe just like keep like bouncing around. So you're taking like very, very large steps. So the gradient, so the slope is just telling you the direction you should move in locally to make the loss go down. But if you take a very large step, then you might actually make the loss go up. So as an example, with large gamma. So it could be something like this. So you want to move. Let's see. Yeah, I guess I guess this is a reasonable example. So if you start off over here, if you make a small step, which would be to the right if you follow the negative of the slope, then you make progress in terms of decreasing the training loss. But if you take a really large step, then you might end up somewhere over here. And then if you keep doing this, you might converge maybe to this point eventually, or maybe you just keep bouncing around. So yeah, I guess you have to be slightly careful about choosing the value of gamma. There's some like nice theory. So if you know things about your training loss, so if you know its gradients and its like second derivatives, if you know bounds basically on how quickly it changes, then you can use that to pick gamma. In practice, it's not often known, so it's hard to use that theory, but at least, yeah, theoretically there's some kind of good choice of gamma. Good in the sense that you make progress, but you don't like jump around. But that assumes that you have some knowledge about the gradients and the curvature of the loss landscape. Question?
Could you combine that with the random search and like put a bunch of start with kind of a bunch of different points and
Yeah.
kind of do this?
Yeah, good. So I guess I mean, you kind of mentioned this already. So the challenge with gradient descent is that you can get stuck in local optima. So you make progress locally. So I guess this is an example. So you make progress. So maybe you start off over here. You take some gradient steps, so that keeps moving you to the right. And then eventually you kind of converge to this point. But this point doesn't have as low as a training loss as this point over here. So ideally you would have wanted to end up here. So yeah, I guess there are a couple of strategies. So one strategy is to combine with random search. So you run that loop many times with different randomly chosen initializations, and maybe you get lucky or at the very least you can just like pick the setting that gives you the lowest loss. Question?
If your step size is too big, couldn't you just spiral out entirely?
Yeah, if your step size is too big, you can definitely spiral out entirely. I guess what I was saying here is that like you pick like a reasonable step size, like a small step size, and then run that loop for different initializations. So maybe one of the loops gets initialized here, you end up over here. Maybe one of the loops gets initialized here, and then maybe you end up here. But yeah, I guess that's kind of assuming that you've chosen a step size that's not too large, and so you're not always like jumping around like crazy. Okay, yeah, there are other strategies as well, like just some other, let's say like clever initialization. So if you happen to know like some kind of reasonably good setting for W, then you can just initialize it close to where you think it might be good, and then let gradient descent do the rest. So that assumes some other kind of like prior knowledge that you have about functions that might be good. It turns out, I guess, one of the like really kind of mysteries or amazing things about deep learning. So when we talk about multi-layer networks, or really, really large networks, like not in the case which we're looking at right now with a single layer, For really large neural networks, it turns out that this is not that much of a challenge in practice. And yeah, I guess people have some like theory around why it's not really a challenge. I guess one theory has to do with like the convexity or the non-convexity of this loss landscape. So this is a non-convex landscape, so it's got like multiple local minima, and the local minima are like pretty different from each other, right? So this minimum is like pretty different from this one. There's some, I guess, theory that tries to explain the empirical phenomenon that if you just run gradient descent, or like some variance of gradient descent that I'll describe in a bit, for deep neural networks, for really, really large, like over-parameterized neural networks, then it tends to find local minima that are actually either close to global minima or are actually the global minima. So I guess that was initially an empirical observation that like training with very large neural networks seems to make the optimization problem easier. And then there's some recent theory around trying to explain why that might be the case. Question?
When you're doing the random search, you set like constraints, right? And so you're only, are you only doing gradient descent within like a given?
So with the random search, you don't necessarily have to have constraints. Like you can choose like a Gaussian, let's say, on the weight W, and then sample from that Gaussian. And then I guess what we're doing is like sampling the initial values, right? And then running gradient descent from each of those randomly sampled initial values. So there's no constraints necessarily here. Yeah. All right, other questions? Okay, I guess if you're interested, this is like way beyond the scope of this course, but if you're interested in like some of the theory of like modern kind of deep learning optimization, probably the place to start is neural tangent kernels. So this has been like one of the big, I guess, developments in theoretical machine learning over the last like 5 years or so. It doesn't fully explain the empirical phenomenon I was talking about, like that optimization for really large neural networks seems to not suffer from this problem of getting stuck in local minimum, but yeah, it makes some good progress. But yeah, I guess if you're interested, but we're not gonna really have time to cover that. All right, so yeah, I guess let's think about the more general case. When W is a vector, so some high dimensional vector, same dimension as the input x. So in this case, what we can do is replace the derivative with a gradient and keep the general structure of the algorithm exactly the same. So yeah, we still want to find some W and B that minimizes our training loss. So again, just for the sake of pictures, I'll draw things as if they were scalar, but think of the x-axis now as maybe containing both W and B. The y-axis is the loss. Yeah, really, it's not just one x-axis. The domain is like very high dimensional if you're working with images. So I guess just a piece of notation. So I'll define W hat. Oh, sorry, not W hat. W tilde to be the concatenation of the vector W with the scalar bias term B. And then we can essentially just apply the same process as over there. So gradient descent. It's going to have the same kind of general structure. So for k equal through 1 through some number of iterations. So actually, I'll come back to the number of iterations in just a bit, but let's say we're doing this for some finite number of iterations. We go through this series of steps. So we choose, before this, we choose some random w tilde. So we choose a random initialization for the w and the b. And then we update w tilde. Let me write it like this. W tilde. And then just return w tilde. So I guess I'm abusing notation a little bit. Let me write it up here. So a slight abuse of notation. So I'll write L w tilde. And I guess what I mean here is, so this is the same as the training loss of w and b. It's just more convenient to think about one vector that has all the decision parameters. But yeah, it's the same general structure, right? So we choose some random initialization or some initialization for w tilde, for w and b, and then we do a bunch of updates. So at each iteration, we look at the gradient of the loss function with respect to w tilde, evaluated at w tilde, and then we update. So let me actually, so we evaluate this at the current w tilde, and then we take a step. So we update w tilde in a direction that's negative to the gradient. Gamma is still a scalar. So this is the learning rate again. And I guess the same things we said about the learning rate also apply here. So if you choose it to be really small, then each step is just taking making a small update. So it might take a while to make progress on the training loss. If you take it to be too large, then you might jump around and potentially not even converge. Okay, I guess questions on this? Go ahead.
So the learning rate, is that like equally applied to all the like dimensions of w tilde?
Yeah, good. So the way I've written it here, it's the same learning rate. It's the same gamma applied to each dimension of w tilde. So each dimension of w tilde is taking a step that's proportional to the component of the gradient, and the proportionality constant is gamma for all of the components. In practice, you can have learning rates that are different for each component. The other thing you could do is somehow normalize like w tilde. So you could scale everything so that each component kind of roughly has the same scale. And so in that case, choosing the same gamma for all the components makes sense. So the problem you might have is if, let's say the first component of w tilde has a huge influence on the loss, and the second component has a tiny influence on the loss, then you might want to take a larger step for the second component as compared to the first component. But if you scale the parameters such that they're kind of all roughly commensurate, then using the same gamma for all components makes sense. Yeah, I guess there's various tricks for doing this. I'll mention some variants of gradient descent that people actually use in practice, and we'll come back to this point of choosing the learning rate. Good, other questions? All right, so I guess just maybe let's for a minute think about this for loop. You could replace this with a while loop. So instead of just running this for some finite number of iterations, you can run this until some termination criterion is reached. So we could do while, I guess, something, like the same process, the W tilde is updated as such. So yeah, I guess what would be a good criterion to stop? And like stop the iterations and return some answer. Go ahead.
Like a condition for the while loop? Or
Yeah, so some condition for the while loop, I guess what would be a reasonable choice.
training loss?
Say it again.
Training loss? Like to check if it's below some like,
Yeah, so you could definitely do that. So you could check if the training loss is below some threshold that you set. That could work. The challenge is maybe there's no way to actually achieve that training loss threshold that you set, and so this might never terminate. Sorry, I guess you had your hand up first. Go ahead.
Well, the training loss continues to decrease and it doesn't plateau.
Yeah, exactly. So you could look at the change in the training loss. So for every iteration here, you could keep track of the previous training loss, and you could see how much the training loss is being updated, and you can have a threshold on that. Another, I guess, equivalent way actually is to just look at the norm of the gradient, so the size of the gradient. If that size gets very small, then you terminate as well. So in the kind of 1D picture, if you approach this point over here and you see that the slope is below some threshold that you pick, then you terminate. But yeah, I guess that's kind of similar to saying the next jump, like the next update is going to be small, and then you terminate. All right, other questions on this? Okay. All right, so yes, I think this is like pretty reasonable, right? So what we're doing is at every iteration, we're moving in the direction of steepest descent, like that's the minus of the gradient, and then we keep doing that until we converge or we, I guess, run out of patience. And we get some reasonable answer. So let's think about like what we really need to implement gradient descent. So this makes sense as a kind of general structure, but we need to basically calculate the gradient, right, to implement this the scheme. So how do we compute gradients? So in this kind of supervised learning setting that we're looking at, I mean, there are some pretty standard answers. If we do discuss reinforcement learning, then we'll have a similar algorithm, but calculating the gradients gets much more complicated. But yeah, I guess let's stick to what we're doing now, supervised learning. One option is to calculate, or let's say estimate, gradients numerically. So basically using a finite difference approximation. So yeah, I guess how would this work? How would you implement this? Actually, maybe let me motivate this a bit more. So let's say that your loss function, you don't have some explicit representation for it. So in the example I was describing before, we could like write down the loss function exactly. Like the exact like function that maps W tilde to a loss. But yeah, I guess just for the sake of argument, let's say that you basically have like Oracle access to the loss function. So you can query, so you can give a particular value for W tilde, and you can ask what is my loss function at that W tilde, but you don't have a explicit representation of it. Go ahead.
You can nudge the first element of the W tilde vector, keeping all else constant, keep that difference, and repeat for every consecutive element.
Yeah, good. So for each component, so let me, I guess, write it down. So you look at, so compute the difference between, so L W tilde the loss evaluated at W tilde plus some epsilon, some small perturbation, divided by epsilon, where the vector epsilon is a bunch of zeros, scalar epsilon, and a bunch of zeros. Right, so you perturb some component of the weight vector. You compute the loss at the perturb point, compare that with the original point W tilde, and you divide that by the perturbation amount, which is the epsilon. Right, so I guess if you think back to your multivariate calculus course, like the way gradients were defined is using this, except that you take the limit as epsilon goes to 0. So we're just saying we're going to choose a finite epsilon, non-zero epsilon, and instead of taking the limit, just calculate this quantity for each component, and then the concatenation of all of those gives you the gradient. All right, so I guess this is one way to do things. This might be useful or can be useful under the kind of setting I mentioned, where you don't have an explicit expression for the loss, but you just have like Oracle access. So you can ask what is the loss function at this particular W, and you get some number. One example is if you're doing some kind of optimization with a human in the loop. So you could ask the human, hey, like, how do you like this setting of things? And the human says, yeah, good or bad, or some like number. And then you calculate this kind of, you make some perturbation and you ask the human again, and then you optimize things that way. There are some examples where, I mean, not exactly what I said, but like variants of what I said, where you don't have explicit access to the loss function. This kind of scheme is useful. I guess in the setting that we're looking at, we don't really have this problem. Like we actually can write down what the loss function is. So option 2 yeah, actually, I guess maybe another example that's a bit more practical. So let's say you're doing some kind of optimization process for a legged robot. So I actually did this as an undergrad. I spent many hours like tuning the gait. Well, I guess watching a robot, a legged robot, like a hexapod robot, tune its gait. So gait means like how it walks. So there's a bunch of parameters that define like how the robot walks. And then you set some parameters. So that would be analogous to W tilde here. And the robot does something, right? So it kind of like maybe moves around in some weird way. And then you can calculate some metric. So there's a bunch of options. Cost of transport is one. So that has to do with energy efficiency and like speed. Like it combines energy efficiency with speed. So you want to have the highest speed, but also keep the energy efficiency low. Or you could just look at raw speed, right? Like how quickly did the robot run. In that case, there's no explicit function that we can write down, right? So you can't like analytically compute the gradient. So something like this actually makes sense over there. So you choose some values for parameters that define your gait. You see what the speed was, or what the cost of transport was, and you update them, and then you do this kind of finite difference approximation, and then you can use something like gradient descent. So that's another example. But yeah, in our setting, in this kind of supervised learning setting that we're looking at, we can just calculate gradients analytically. So the training loss we defined as the average loss across our training examples. And so the gradient, which is what we need, L of W tilde, is the gradient of this quantity, so it's 1 over n gradient with respect to W tilde of the loss. So I guess by the linearity of the gradient, I can bring the gradient inside the summation. And then we have an explicit expression, right, for sigma and for the loss. So if we're choosing the sigmoid activation, we can write down exactly what that function is. If we're choosing the binary cross entropy loss, we can write down exactly what the function L is. So we can actually calculate this via the chain rule. Right, so you look at d sigma, dz, and then you look at the gradient of this expression with respect to w and b. So of course you could do this by hand, but yeah, there's some nice automatic differentiation tools. Yeah, I guess all the kind of modern machine learning packages have ways to calculate these gradients analytically, gradients automatically. So if you specify, if you just tell the software package I'm using the binary cross entropy loss, the sigmoid activation, then it basically handles the gradient computation for you. But yeah, I guess under the hood, it's calculating these gradients. All right, so I guess any questions on that? All right, so I guess what are challenges with what I described over here? So one major challenge is one of computational efficiency, right? So the gradient descent procedure that I described over here requires the computation of the gradient for each term in the summation. So each term in the summation corresponds to a particular example in your training data set. So for each example in your training data set, you need to calculate and I guess evaluate the gradient of the loss with respect to your parameters, and then evaluate that gradient at the current setting of parameters. So this can be pretty computationally expensive. For large data sets. Because we basically have to loop over, or at least like evaluate like all the gradients for all the training examples. And if we have lots and lots of training examples, then this can be quite computationally challenging to do. So I guess one variant of gradient descent is what's known as stochastic gradient descent. Abbreviated as SGD. Which kind of gets around, well, it has two benefits. So one is kind of the direct benefit, which has to do with computational efficiency. There's a side benefit, which is much more subtle, that I'll get to in a bit. But yeah, I guess let's just describe what stochastic gradient descent does. Another name for this, it's not used as commonly, but like mini batch gradient descent. Yeah, usually people just call this stochastic gradient descent. So yeah, with SGD, what we're going to do is, instead of evaluating the gradient for all of the examples in your training data set, we're just going to randomly sample some fraction of the examples and evaluate evaluate the gradients for that randomly sampled batch, that randomly sampled subset, and then keep randomly selecting some proportion of the data at every iteration. So yeah, let's write down the steps in the algorithm. So again, as before, we're just going to choose some W tilde, like to initialize everything with. So yeah, maybe we just choose it randomly. And then we execute this for loop. And again, you can replace this for loop with a while loop, where you check some of the conditions that we discussed before. So what we're going to do in the while loop is we're going to randomly sample capital B examples from our training data set. I guess by randomly, I just mean like uniformly randomly sample B examples. I'll say a bit about the choice of B, but think of B as just some number that's less than capital N, where capital N is the total number of examples in your training data set. And then we're going to define L hat of W tilde, which is going to be the average training loss. So I won't write down the whole expression here, but this is the average training loss on the B examples that we randomly chose in step 3. And then I guess we just apply gradient descent. Sorry, question, yes. Sorry, just say that one more time. Yeah. Yeah, good. So I guess I mentioned that there's like two benefits to stochastic gradient descent. So what I'm describing now is just the kind of computational benefits. That's the most direct one. What you're saying is also true, and I'll get to that in just a minute. Maybe let me just I'll write down the steps, and then we'll get to that. That point is much more subtle and much less theoretically well understood. But yeah, I'll get to it in a second. All right. So yeah, we define the loss L hat across the randomly selected batch subset of examples, and then we compute the gradient of L hat with respect to W tilde, and then we update W tilde. And then just return W tilde. Actually, sorry, I keep forgetting the evaluation. So we just evaluate at the current setting of W tilde. So it's the same exact kind of structure, or almost exactly the same structure. We're still taking steps in the direction that's opposite the gradient. We still have this learning rate gamma. The only difference is every iteration in our for loop, instead of evaluating the gradient for all of the examples and then summing those up, we're just randomly selecting some proportion, B over N of examples from the data set. And that random set we keep changing. Like every time we randomly select some examples and then run this gradient descent procedure using just those examples. And yeah, typically, I guess you would choose maybe like, I don't know, 20% or so of examples. Like partly this depends on like how large your training data set, how much computation you have access to. So if you have a certain budget for computation, then you can use that to select the choice of B. But yeah, something like 20% or so can work in practice. And yeah, I guess what this does, like most directly, is that it improves the computational efficiency, right? So we've reduced the number of like gradient calculations we're doing at each step. So we're just using a batch of B examples to do the updates. The second point, which is, yeah, I guess much, actually, is that point clear? Any questions on that? All right, yeah, the second point, which is more subtle, and so empirically it seems to be true. I think theoretically there's some papers which, yeah, I'm happy to point you to, some like theory, but not 100% satisfactory, I think. But so there's basically, yeah, two benefits. Actually, all right, there's really three benefits. So the most direct one, I mean, there's no question about this one, is computational efficiency. Yeah, each iteration requires significantly less work than gradient descent. It could still be that the number of steps you need to make to converge to something good, like maybe it'll be larger potentially, but at least each step is less computation than if you were doing the full version of gradient descent. The second potential benefit, which seems to be kind of empirically valid for deep learning, is that you could jump out of local minima. So because there's like this kind of inherent like randomness in the steps that you're making, yeah, this is, all right, let me draw the one-dimensional version of the picture. So with the standard gradient descent, like you're just going down the slope and you're going to converge to this point. There's no randomness in the process except for the random initialization. But with stochastic gradient descent, you're not going down exactly the slope, right? You're not taking a step that's kind of exactly aligned with minus of the gradient, because the gradient you're calculating stochastically. You're just computing an approximation of the gradient using some finite number of examples. So it could be that you basically like jump out. So instead of converging to this solution, you maybe jump out and then you end up over here, and then you end up converging to this. And this could happen, I guess, do people have intuitions for why it might happen, or if you have a question, go ahead.
Well, could you just as easily jump into areas and be stuck in them?
You could also jump into areas that, the opposite could also be true. So there's some, so I guess this is what I was saying, it's not totally clear like exactly why this is a benefit, right? So it seems to help, like it seems to be the case that the kinds of solutions that you get with stochastic gradient descent seem to be better than just doing gradient descent. So let me add the third point, because like 2 and 3 are kind of coupled, which is that you could get better generalization. So we haven't really talked about generalization yet. We're going to spend some time talking about it much more deeply in the next lecture. I kind of briefly mentioned it in the previous lecture. So optimizing the training loss is kind of just a surrogate for what we actually want. So we already have the training data set, right? Like we don't need to like know the labels for the training data set. We already have this data. What we need is examples or labels for future examples that are not part of our training data set. So that's what I mean by generalization. So doing well on examples that were not part of the training data set. And yeah, I guess empirically at least, it seems like using stochastic gradient descent seems to help with better generalization. I won't go into I guess since we haven't really talked much about generalization yet, I won't go into the details, but the rough intuition is that you can basically jump out of minima that are very sharp. So if you're using gradient descent, so not the stochastic version, if you start up over here, you might end up over here. But if you're using stochastic gradient descent, because of the randomness, like this is kind of a sharp valley, you might jump out and end up over here. And this is like a wider local minimum, like wider in the sense that it's not as like sharp as this one. The curvature here is smaller than the curvature here. And I guess there's some intuition for why, even if these have the exact same training loss, like this point and this point have the exact same training loss, the wider one tends to generalize better, like do well on examples that are not part of your training data set. Yeah, like I said, that story is like much more subtle. We'll spend more time thinking about generalization in the next lecture. Yeah, I guess does this kind of maybe partially address your question?
Yes, I think that if you consider like examples that are not necessarily in your distribution or in the wider valley, then it's almost like there are like parameters that are around the optimal parameters.
Yeah. That is still pretty good. Yeah, that's reasonable intuition. Yeah, and there's some theory, but like I said, not super satisfactory theory. Question.
So, from what I understand, then we have the underlying assumptions here that the more stable optimum
Yeah.
is somehow, in general, better out of distribution.
Or not even necessarily out of distribution, even just other examples. Yeah, that are not in the training data set. What I'm saying is just intuition. There are like papers that try to formalize this. If you're interested, this is like way beyond the scope of this course, but yeah, I guess if you're interested, there's a person at TTI, the Toyota Technology Institute, Nati, Srebro. Yeah, he's done a bunch of work on trying to understand this like phenomenon, like understanding why. Sorry, not here, this picture over here, like why flatter minima tend to generalize better. There's a bunch of kind of other people as well. But yeah, I guess his work, he gave a talk a couple of years ago, so I remember his work. If you're interested, yeah, take a look at that. Question?
Yeah, just for like clarification, so you're saying that, so basically you're saying that even if we have like two like minima that are like, at the same point, the wider one is going to generalize better for samples not
in the training data set, yeah. I guess I don't want to harp too much on the generalization point just yet, because we're going to spend much more time in the next lecture talking about generalization. So maybe we can revisit this question in the next lecture. But I guess maybe just take it on faith or look at some of this work that I mentioned. But yeah, it seems like definitely this is true, and then empirically, at least as of right now, like 2022, it seems like these things empirically are also true, and there's some theory around it. All right, other questions? Go ahead.
Is there a way we can put bounds on the samples that were, like for number 3, step 3 of the, like stochastic gradient descent? Like when we're randomly sampling
Yeah.
views, can we put ranges for which we would sample within? Or specify that we don't get like the wrong, like we don't end up in the wrong minimum.
Oh, I see. That, I don't know how to do that. Like how to choose the examples such that you end up at somehow a better minimum. Yeah, I don't know how to do that. That's an interesting idea. Yeah, I mean, typically what people do is just like randomly select some fraction of the training examples and use that. But yeah, maybe there's some kind of clever algorithm that better selects the examples that you use. Yeah, that's a good question. I don't know people who have looked into that. Cool. All right. So I guess, let me see how we're doing on time. So about 10 minutes. All right, so stochastic gradient descent is kind of the algorithmic like workhorse in terms of optimization for deep learning. There are some other like bells and whistles. So in practice, the variant of stochastic gradient descent that is most widely used is called Adam. So yeah, I guess this was proposed, this algorithm was proposed maybe 7 or so years ago. And yeah, if you look at the Adam paper, it has some like absurd number of citations. I have no idea what it is anymore, like tens of thousands of citations. Yeah, it's the most like popular algorithm for doing optimization in deep learning. So basically what it does is also like adaptively chooses the learning rate. So in what I described so far, we just choose some learning rate that's fixed. Adam has a way of choosing the learning rate, kind of adaptively changing the learning rate based on the statistics of the gradients that are being calculated. The basic, I mean, it's still using like stochastic gradient descent, but with this like addition of choosing the learning rate more carefully. The other, I guess, thing I'll mention is GPUs. So graphical processing units. When we run stochastic gradient descent, a lot of the computations are parallelizable, right? So each term in the summation you can calculate independently of every other term, and then you can sum up those together, and that's the kind of computation that GPUs are particularly good at. So relatively kind of simple calculations that you can do in parallel. So that tends to significantly boost the computational, or significantly boost the computation time, significantly reduce the computation time in practice. All right. All right, I guess any other questions on the optimization part? Okay. So the last thing I want to talk about, so this is just a preview, we'll talk more about this later, is going beyond single layer neural networks to multi-layer networks. I mean, the basic idea is fairly straightforward. Like, we're just going to stack a bunch of single layer networks together, and so on. until we get some output. So the input is, again, some image, let's say, some vector x. The output, we can call it y. And each intermediate thing is a hidden layer, so h1, h2, and so on until you get to the output layer y. So that's I guess the general picture. I'll write down the exact computations. So the steps for calculating the output are as follows. So h1, the output of the first hidden layer, looks very similar to just a single layer calculation, single layer neural network. But with a couple of modifications. So each of these, like HIs, is going to be a vector. And so we have instead of just a kind of vector weight, we have a weight matrix. And then instead of a scalar bias term, we have a vector bias term. So let's say like x has dimension n by 1. Let me see if I wrote down the dimensions explicitly. No. Okay, so W1 transpose will have dimension, let's say like D1 by n, and then this has dimension D1. So what we end up with once we do this calculation is D1 by 1, D1 by 1 vector. Right, so that's H1. So W1, I guess just to be explicit, so W1 here has dimension n by D1, and so W1 transpose has dimension D1 by n. Right, so that's the first computation. So we start with the input, which is a vector. We do this computation. Sigma here is some element-wise nonlinearity. Right, the thing inside sigma is a d by 1 vector, so we apply a nonlinear function like sigmoid or ReLU or any of the other choices to each component individually to this like vector d1 by 1 vector. And then we repeat this computation. So H2 is sigma of W2 transpose H1. Let me just call this B1, so plus B2, and so on. So H, let's say K is sigma WK transpose HK minus 1 plus BK. And finally, the output Y. You repeat the same computation again. So W, let's say K plus 1 transpose HK plus B K plus 1. And the way I've written this here, Y need not be a scalar. So it could be that Y, like the label, is itself some vector. It could be a scalar, in which case you just have to make sure that the weight kind of matrices give you a scalar at the end over there. So you might have a vector weight instead of a matrix weight. But yeah, it just depends on exactly what the label is. All right, so I guess that's the rough structure. So we're just repeatedly applying a single layer computation over and over again So we end up with these like intermediate representations, and then like finally get some predicted label y. So I'll say much more about, I guess, why this might make sense. Like the rough intuition is that this can represent, like this process can represent functions that are nonlinear in X. And so we're no longer limited to just the kind of linear classification or like template matching that we were doing with a single layer network. What I've described here, this kind of general like computation, is a multi-layer perceptron, MLP. So this is kind of just a generic architecture that I've written down over here. If you make more, or if you add more structure to the weights, then you get like different architectures, like convolutional neural nets, and we'll spend some time talking about those as well. But all right, I guess that's a preview of what we're going to talk about. Any questions on this computation? What's going on here? Question here?
Yeah, so is the dimensions of like x bar, like the original input and of like h, like they don't have to be like the same?
Yeah, good. So they don't have to be the same. So it could be that we're starting with some like dimensions of the input, and then we're making the representation have a larger dimension, and then going back down again to the whatever the label dimension needs to be. Yeah, so it could be that the dimension is increasing or decreasing, and yeah, any of those is kind of valid from this architecture. Yep. Good. Other questions? All right. So I guess what we're going to do in the next lecture is say a bit more about like multi-layer networks, talk a bit about how to optimize them, and then spend time thinking about this question of generalization as well. All right. So I think everyone knows this, but I guess some people asked me at the beginning of the lecture. So there's no class for us on Tuesday. Like Princeton is following a Friday schedule on Tuesday. So yeah, enjoy your Thanksgiving, and I'll see you after.